All right, guys, we're doing a little science experiment. Most of you probably already would figure this is the case or just common sense, but it's just interesting to look at it and point it out. Kind of zoom in on it, shine the magnifying glass on it, as it were, just to show you. This is a 200 spine arrow shaft. If you can read that. And this is a barbecue skewer. And it's only about a foot long, maybe a little more. And the spine on this is pretty flexible. I mean, I'm barely pushing on it. And it's giving pretty bad. Whereas the 200 spine, I think this is a 29, 30-inch long shaft. So we could even cut it down 2 inches or so, but I'm pushing on it. And definitely does not want to give, if you can see that. I'm really pushing on it. The give is minimum. Whereas you're pushing on this, I mean, that's pretty bad. So, however, the interesting thing, when we're talking about penetration, stiffness is important, right? But so is a smaller frontal surface area. Now look at these two. I mean, the frontal surface area is insane. For the skewer, I think this is like a 0.09 inch diameter skewer, 0.08 maybe. Whereas this shaft is, well, it's a micro diameter arrow, 200 spines, so the outer diameter arrow of the shaft is about 0.256, so a little over a quarter inch. But the head is like 0.3 something. It's over 3 inches, or it's over 0.3 inches. So that is like over 3 times the surface area. And we're gonna watch, because if this was all we were comparing, all else equal, this would be a lot easier to penetrate a medium than this. But now that we have the spine flexibility factor taken into account, even if we assume perfect arrow flight, let's just say these are both arrows, watch what happens. We're just going to push this into a foam target medium. Physics would say the faster the arrow, right, the more resistance. Slower the arrow, less resistance. So we're just going to push it in. Very little resistance, velocity speaking. So you can kind of see this. I'll try and put my hand there so it's easier to see. Okay, pushing from the knock side, the rear end. I mean, look at how much we're bending, and then it would bend up. And we've bent the shaft essentially, but I mean, we're tearing. We're not even, we look at that, what's called an effective frontal surface area we're creating. So small diameter, right? Less resistance, not when it's so weak. We're creating much more resistance. Okay, now, I mean, look at that, that's all bent up. Now let's compare that to a super stiff 200 spine carbon arrow, pushing from the knock in. Okay, I'm gonna hold the target down just so it doesn't push it back. But you can see it's not yawing. Even when I force it to yaw, I mean, it doesn't bend hardly at all. And it's in without any bending. And I'm even pushing the knock end really. Let's bring it out again. I mean, there's like no flex on impact. The whole thing either wants to move. There's no flex. There's no buckling. So that just kind of demonstrates to you when you go too high in the spine number, so a weaker shaft, a weaker spine, it just goes to show that even if it's a smaller outside diameter, smaller frontal surface area, it's going to flex. So geometrically, it's a lower frontal surface area. Effectively, once at impact, it's going to buckle and flex and it's not going to have straight alignment. And so that buckling and flexing and yawing is actually going to create a greater, what's called an effective frontal surface area, even though it's got a smaller geometric frontal surface area. And that effective frontal surface area, as you can see right here, there's a 200 spine. And I was flexing on it and it just stayed straight. And this, from here to there, is the surface area that was created from this when I was trying to push it in and it was flexing. And so even though it's geometrically, this small needle-tipped diameter shaft is geometrically smaller in its frontal surface area, it's effectively larger than the 200 spine arrow when this is pushing straight, because it doesn't have that flex and buckle and give when it's going into the target. It's geometrically larger in its frontal surface area, but effectively smaller in its frontal surface area due to its stiffness and spine and ability to maintain perfect axial alignment through penetration. And because of that, it acts as if it's geometrically a smaller frontal surface area penetrating object.